Hello, my name is Robin Mitchell, and today Electropages is here at Embedded World Nuremberg 2023. Today I'm joined by Flavio from Coilcraft to look at the new software which they're coming to offer. And thank you for having us.
Thank you. Welcome at our booth. It will be a pleasure to show yourself and our audience the new tool. It's a part of something we were working on really very recently to help engineers to search and find the best solution for power inductors with a few steps in a few iterations so they can judge based on numbers and not just on guess what is needed for them for their solution.
Brilliant. So one thing that I know when it comes to inductors is that they're not the easiest things to calculate, to figure out which one you need.
Yeah, a lot of engineers are always struggling because of course this is one of fundamental parts of the power supply. Locate the proper part in terms of dimension, in terms of efficiency, in terms of overall performance is of course optimized by cost. So the scope and the goal of this tool is exactly working in a natural way, in a fast way to locate the most suitable part through a few steps. Actually, I can show you how it is easy to go through the tool.
Please
under Coilcraft. This is coilcraft.com, our main page. Just clicking on design tools. Yes, exactly. Over there. Scrolling a little bit down, I'm showing you how to say the most comprehensive tool. There are other entry points, but maybe I will tell you more another time. Here we focus on the most comprehensive one. Actually, this is the DC-DC Optimiser. All these tools, they go under the name Mag Pro, Magnetic Pro. It's a trademark we registered to, how to say, give a name to our suite of different tools because we have also other categories of products for radio frequency, common mode choke and so on, and each category has its own tool. So this is a variety. Today we focus on the most comprehensive for DC-DC converter application and then power inductor finder. So we click on DC-DC Optimiser. Actually, you see it's very fast. 3 tabs here on the top, depending on the topology you would like to work on. Back topology, boost topology, and back boost topology. Actually, the most popular one is back topology. As you can see, it's a simplified circuit for a back inductor. What is
all
required?
the main things here.
Right, exactly. These are, as you can recognize, the parameter of the DC-DC converter. So the basic one, you are absolutely requested to fill, to calculate which is the inductance required. Voltage in, voltage out, current output, switching frequency. Those are the voltage drops on the diode and on the switching and the ambient temperature.
So could you describe here what's going on with this optional section?
Oh yes, of course. Actually, this is the box related to the ripple information. We keep it optional because we give the freedom to the engineers to type in either what they like or leave it empty. So if it's left empty, the tool will locate the proper inductance calculated with the numbers above, and then checking what it would be the ripple for all the possibilities into the whole database of parts that will withstand those working conditions.
And I suppose that the reason why ripple is also optional is because ripple is not that bad at times. So a lot of the times you'll have a switch mode power supply and then you'll have a linear regulator to make it smooth. So it's not too essential, the ripple. Well,
actually, the typical rule of thumb would say to keep it about 30% of the current. That will be kind of a safe solution to avoid big spikes. That would involve EMI issues. But anyway, sometimes it's nice to push a little bit harder, because pushing it harder, it means to locate maybe solutions that are a smaller form factor that will be not located if we put that number over there. And so it's a sort of possibility to have a wider view in the surrounding and then accepting something that we might cut,
Yeah.
putting that a number over there. So in fact, this time we leave it open, not thickened, and we try to get an example for example, a data center power supply, where typically you have 48 volts, maximum 54 volts. You want to go down to 12 volts for an 8 ampere part. Roughly it's a 100 watt power supply, and actually you operate a kind of 300 kilohertz, room temperature 25. We leave it empty, and let's see what the tool is telling us.
And this way, the engineer doesn't have to do the calculation himself.
No, actually everything is done by the tool, and the data you see here displayed are measured and verified by an equipment back at corporate. So all inductors are characterized, and these are real numbers.
Oh, wow.
Yes, it's really very nice. So what is telling us this tool? Actually, the part we would need is something, as you see, kind of long list of parts. So far we go down here the list, and we have 238 parts that would fulfill the job with, how to say, different total losses, different ripple. So we need to shrink a little bit the selection. And actually what we can do, for example, we want to for sure look at shielded part, so no emission.
Yeah, of course.
Eventually we want to have them SMD. Let's put a little bit a limit to this ripple, because as you can see, it can go as very huge.
This delta ripple here, is that number based on our calculation here?
Exactly.
Ah, so it's not just about the part, but it relates to what we.
Exactly.
That's brilliant. That is.
That's exactly what it means. So with this operating condition in the back converter, using this part, it will operate with that ripple.
That's brilliant. And just by doing that, the engineer can save so much time when it comes to choosing their part.
Exactly. So here you have really the widest overview possible. Then you say, for example, let's leave it 45, let's say, okay. Then, how to say here, another thing we can consider is the maximum temperature of the part to stay on the safe side. Let's say something like, I don't know, 75 degrees C maximum. And now, okay, you see from 238, now we are down to 33.
Yeah.
What else we can do? As we are talking about data center application, you might understand that those power supply, they go in on racks, and they have some limitation on height.
So it can't be too high. So
exactly. So the part can be too high. And then we come here, and we limit this to 10.5.
Because 20 was a bit high.
Yeah, exactly.
That's like sticking about that much above the board.
Yeah, maybe from 6 millimeter to 10.5. And here you go. Then the parts are ranked here by the smallest footprint and height. And as you can see, we have the 10 millimeter, we have the 15 millimeter. Maybe we can go even lower. So let's review, for example, this, and see, instead of saying 45, let's put double, 80. What happens? Now you see appearing also 6 millimeter part tall.
So what we're basically seeing here is that you can sacrifice some aspects of your design to improve in others. So for example here, we make the ripple worse, but we can get a smaller part.
Yeah, exactly. Everything is interacting, all the parameters. So, yes, how to say, relaxing one parameter
Yeah.
can have a beneficial effect on others.
Yeah.
In this case, allowing a higher ripple, we could go down with the height and eventually taking the 6 mm part into the game.
Yeah.
And now we can just focus on what we got here.
Because before that's gone from 10 millimeters to 6 millimeters, hasn't it?
Yes.
It's a substantial.
Yeah,
reduction in
exactly.
height.
Exactly. 4 mm less in the height can be quite relevant.
Would it be less? It'd have less mass as well, wouldn't it? It'd be a lot lighter. I think.
Well, in this case, it's very much the form factor. I wouldn't say that there is a big impact on the weight, on the mass, because it has the same footprint, and there is only 4 mm difference in height. But that can be fundamental if you want to be very, very low profile.
Yeah.
But let's go further down and consider, for example, this new option, 10 by 10 by 6 mm, 10 micro, with another possibility, same form factor footprint, 10 mm square, but 10 mm tall, same inductance, and the analyzing graph, seeking the box here on the left side.
So you can select the coils.
Exactly,
Then, yeah.
exactly. Then analyze and graph, you go into the final page, let's say, where what you find actually.
That's brilliant.
Yes,
That is
Yes.
brilliant.
that's exactly the triangle curves you would see
bloody hell.
on an analyzer, and this is the square voltage input for.
You must be very proud of this.
Yeah. That's
Blimey.
absolutely a very effective tool. We work a lot. This is, how to say, we call it a tool from engineers to engineers.
Absolutely.
It comes from really several interaction and talks
And
with engineers.
you really help the customers with this kind of technology.
Yes.
You really do.
From a first side, actually, just checking the efficiency, not going farther down.
Yeah.
You take a look at these bars here, and you see that the 1060 6 mm tall part, it has 2.5 watt losses, total losses. The black bar is the content of core plus IC. That's how the machine characterizes the losses related to core IC. They are together. And the light gray one is the content of DC losses. And as you can see, the different impact of the DC losses for a smaller height part. You have higher DC losses, higher resistance of the copper wire, and that has this impact. It's about 0.5 watt more.
This is quite significant.
Yeah, exactly. But actually, what I can say, an engineer needs number to decide if sacrificing this how to say losses, 0.5 watt more, would allow the 6 mm tall part.
Yeah.
So you have to judge like that. And also another point, looking at this temperature rise versus current, it tells you how fast the temperature of the part will rise, increasing the current. And
brilliant.
Browsing over the current, you will see number increasing.
Yeah.
So you can have an overlook also nearby how the temperature behavior of the part will be.
It's non-linear. That's interesting.
Yeah, exactly. That's not linear.
Ah.
Some of those parts, they have also large copper wire, and it helps to dissipate the heat from the part. So they are also very efficient to cool it down by themselves. The two parts will operate at ambient temperature. The larger one, or the taller one, let's say 54 degrees C, and the shorter one 69 degrees C. But this is done at ambient temperature 25.
So you can slide the temperature.
I can slide up to
that's
125 or whatever ambient temperature.
Let's do 75 then. It's only two. It's
Oh
fine.
yes, about that, okay?
Yeah.
And then the tool is thinking and recalculating.
Oh, do you click update or do we have to?
Oh, that's interesting. No matches. Why that?
Because we went over the temperature, didn't we?
Exactly.
Yes, because we specified 75, didn't we?
Yes.
So we just hit
too
set.
much temperature by the current and by the
Yeah.
part.
So we have to change that temperature back.
Exactly. We have to go back. That's an interesting exercise. This cursor here, it helps you to judge if this solution will still be good,
Yeah.
changing the ambient temperature. Of course, now we type a certain maximum temperature, like 75 degrees C. Moving high, the temperature at other 70 degrees C, the part will probably both parts will their maximum total operating temperature, and then the part want.
Yeah.
So I recommend before entering into this selection, probably it's better to change the ambient temperature in advance when we have the longer list, and then we will see who's going to survive. Here is interesting to note what we have seen so far, the temperature rise, the total losses, and also something that might be relevant to show to our audience is explore losses. So it's another tab farther down. So sometimes what you can judge is the boundary condition. So what it happens if I might change ripple more than what I decided at the beginning to my total losses. So this graph is here is a total losses versus ripple, and the right graph is total losses versus frequency. As you can see here, if my ripple is going up from 3 ampere to 3.5 ampere, actually you have numbers here, what it would be my total losses. So you can judge if you can even push further this ripple into your parts and what they are going to pay in terms of efficiency. Or as well, we said we start operating at 300 kilohertz, but maybe I can decide to move to 400 kilohertz, and then the tool is automatically calculating what it will be the total losses operating at higher switching frequency. And if you are not happy, you can also type whatever range here on the top, and you can adjust the graph by the window you want to see. That's really what we think really very complete analysis. Once you are happy with the solution, there is two things I want to say. First one, how you can export the analysis you have done so far. You can email it, copying the link to an email, and it goes.
And that will share all the graphs and the details.
Exactly.
Oh, nice.
This link is exactly taking you to this page, so your teammate or your final customer can exactly see what you were analyzing, or you can export a PDF or print or an Excel spreadsheet.
And that's very good for documentation.
Exactly. Automatically, you can remember all the steps you have done and why. And also here, you have these two tabs, sample. It takes to a sample request. You can add whatever quantity, usually up to 10 is free of charge. And you can add to cart and get free samples from us.
That's pretty generous.
Yeah. We are really very generous as a company. We support really in an open way this testing because people need to receive a part and test themselves. So this is a kind of very fast iteration tool, we think, and very comprehensive. There are other opportunities, of course. Just briefly, Finder and Analyzer. Maybe you search nominal inductance, whatever, I don't know, 4.7. To ampere, and then you put 1 megahertz, find it, This is the typical finder and analyzer. Maybe you want to compare inductors from a competitor, which gives just simple data sheet with nominal inductors. Actually, you come here. Or another solution may be this one. Search for inductance at current, because actually it happens that your inductor will operate at a certain current and you want to have a minimum inductance at that current. And this is what it does the job.
Is that because if you put too much current through an inductor, you saturate it?
Exactly.
Yeah.
Exactly. You want to be sure that your part would have a minimum inductance at that current and it won't saturate. So that's what you do. Or you simple one, compare the losses. So at a certain frequency, ambient temperature or whatever temperature, you know already what families are from us. For example, I'm scrolling down to the latest XGL 6060. I don't know, kind of 3.3. And again, so just giving you a real example, 50-50. So the first one is 6 millimeter square by 6 millimeter tall. The second one is 5 millimeter square by 5 millimeter tall. Same inductance. So let's see how it works. Current, let's put, I don't know, 3 ampere. Ripple, let's use the typical 30%. Let's see how it works. Here you go. You come to a page which is now familiar to you. What's the difference? Actually, we didn't say the voltage in and voltage out data in duty cycle. It's not calculated. So it's 50% duty cycle curve. But again, you have the familiar losses graph, bar graph, and essentially it's telling you that the smallest part is 120 milliwatt versus 75 milliwatt, and you have all the stuff we used to see from a previous presentation. And again, here you can go 85 ambient. Let's see, it's still good because the part is only 88 degrees C or 86 degrees C versus an operative of 165. So we can push further. Let's see, 125. Let's see where we are. Let's see if I'm able. Yeah, here you go. The part is still good. It's quite hot, but not exceeding the maximum temperature. It's 130 degrees C.
So that's the temperature of the part at that ambient temperature.
Right, exactly. So you can exactly duplicate the working and operating condition of your DC-DC converter and judge if this part will be good. Probably you can try also to have a smaller part.
Yeah.
A slightly smaller form factor, or maybe trying to reduce the height and see if you can save something and do simple iteration and come to an easy conclusion.
Oh, brilliant. Brilliant.
So this is the same tool, different entry points, depending how much you know about the parts, or if you are starting from scratch, let's say, from the basic.
And so using these tools, engineers can find the perfect inductor for their solution.
Very easily. They don't have to remember what material they need or what material is done. In this case, it's said here it's composite.
But we don't care about that.
You don't care, actually.
Because we just want to make sure it's going to work in that. And then you're deciding the technology for us.
Exactly, exactly. That's the point. You don't have to remember the acronym, or if there is something new, it shows naturally up here.
Yeah.
Because it's selected by your parameters.
Brilliant. That's fantastic. So now that you've demonstrated the software on Coilcraft, if an engineer out there wanted to use your system and wanted to get in contact with Coilcraft, what's the best thing that they can do?
Well, actually, everything is on coilcraft.com, but we have really a lot of direct personnel and engineers on the field, and you can easily get in contact with us directly, just typing in a mailbox and we will answer really very short. We have people checking constantly the mailbox, and they will send directly your inquiry through the proper person, and we will follow up directly,
Brilliant.
locally.
Well, thank you ever
Everywhere.
so much for taking the time to join us today.
It was a pleasure having you here. Thank you so
Absolutely.
much.
Thank you.